Hello everyone, welcome to this video. In the previous video, I have explained the chapter 1 power supplies. In that chapter 1, we have discussed different types of rectifiers and then voltage regulator, voltage multipliers. The chapter 2 dealing with amplifiers. Here we need to understand the different types of amplifiers and the amplifier characteristics, gain, input-output resistance, frequency response, bandwidth, phase shift, and negative feedback and multistage amplifiers. For this chapter, we are going to refer chapter 7 in Mike Tooley Electronic Circuits Fundamentals and Applications textbook. So these are the contents I am going to cover in this video. First, what is an amplifier? Amplifier is an electronic device that can increase the power of the signal, or we can say amplifier circuit is going to increase the strength of the signal. So if you apply a small voltage signal like this to an amplifier, the output will be a large signal you can observe here. So amplifier is going to increase the voltage or the power of the signal. So we say the output of the amplifier is V out will be equal to AV times V in. What is AV here? AV is the gain of the amplifier. The amount of amplification it is produced is called as gain. So the expression for gain can be written as V out divided by V input. This is the practical example of an amplifier device we are going to use. A microphone, it takes an audio input. That audio will be having a less voltage. So that will be connected to an amplifier. Amplifier will increase the strength of the signal and it will be given to the speaker, where the speaker output can reach to the maximum distance. So next we have type of amplifiers. We need to understand the different types of amplifier circuits available. One is AC coupled amplifiers. Here we need to understand the coupling. What is coupled amplifier means? Coupled amplifier in the sense we are going to use 2 or 3 or 4 stages of amplifiers connected together one after the other. So in this particular type, AC coupled means only AC component of the signal is going to be transferred from one stage to next stage. Such amplifiers are called as AC coupled amplifiers. Next we have DC coupled amplifiers. Here also the number of stage of amplifiers circuit is there, where both DC and AC component of the signal is going to be transferred from stage to next stage. Then we have large signal amplifiers. These kind of amplifiers is capable of amplifying the large voltage signal or the high current level inputs. If we are going to provide an input typically from 1 volt to 100 volts or more than 100 volts, the amplifier is able to amplify that signal to the next level. That is called large signal amplifiers. And we have small signal amplifiers also. Small signal amplifiers in the sense very low voltage signals or the very low power signals are going to be given as input for the small signal amplifiers. It will amplify that to the next voltages. Also we have audio frequency amplifiers, where the inputs are only the signals which are come under an audio frequency. The audio frequency in the sense it is in between 20 Hz to 20 kHz. The audio signals will be having the frequency in between these two frequencies. Those kind of amplifiers which are going to amplify only audio signals are called audio frequency amplifiers. Wide band amplifiers. Wide band in the sense, as the name itself says, the frequencies which the amplifier is going to amplify is having wide range. Means from 10 Hz to several megahertz of frequencies, the amplifier is capable of amplifying the signal. That is wide band amplifiers. And then radio frequency amplifiers. You might have known the radio frequency will be from 100 kHz to over 1 gigahertz. These range of signals will be called as radio signals. So this radio frequency amplifier is going to amplify that range of signals. Then low frequency amplifiers. Low frequency amplifiers in the sense low noise amplifiers we can call, so that they contribute negligible noise to the signal being amplified. So usually it is having the voltage levels less than 10 millivolts, very less voltage signals we can say. These are the different types of amplifiers available. So what is then amplifier gain? What it means? Gain is an important parameter which can define an amplifier, the amount of amplification it is going to provide. What is the gain we are going to get from the amplifier? That is how we can understand this. So you can observe in the figure here, the diagram, the input we are giving V in is very small, V out is very large. And with respect to the input side is concerned, we have I in, you can observe here, this is input side current, and similarly I out is output side current. So voltage gain in terms of AV, if we write, that is V out divided by V in. V out, output voltage, to the input voltage. Similarly, with respect to current, if we take, that is I out divided by I in. The output current what we get from the amplifier divided by the input current is called current gain. Similarly, we will be having power gain. Power gain is power P is equal to I into V. So we can use that formula here to write the power output as I out into V out divided by P in as I in into V in. So we can write this expression as I out divided by I in separately into V out divided by V in. So we know that I out divided by I in is AI, V out divided by V in is AV. So the power gain AP can be written as AV into AI. Then we have another parameter we need to look at, that is input resistance and output resistance. Input resistance will be an ratio of voltage at the input to the current at the input. V divided by I is the expression for R. We know the same formula here we can use to get the input resistance. R in is equal to V in divided by I in. Similarly, output resistance. Output resistance is the ratio of open circuit output voltage to the short circuit output current. Here you can observe in the diagram, R in and R out are going to be shown with some internal circuitry of the amplifier. So here with respect to the resistance are concerned, we need to note these points. We are not supposed to get confused with the RL connected in the circuitry. This RL is a load resistance, or the resistance of the load what we are going to connect the output of the amplifier. Output resistance is not same as RL. Output resistance is internal to the amplifier and RL is external to the amplifier. And in some cases, when the capacitance comes into picture, the reactance of the input may become large. Means a stray capacitance appears in parallel with the resistance. In such cases, the resistance and the capacitance reactance will be totally called as input impedance, that is represented as Zi. Remember, for any amplifier, input impedance should be high, or the input resistance should be high and output resistance should be low. Similarly, we call that as output impedance. Output impedance should be less. And then frequency response. The frequency response is a curve here. You can observe it is plotted gain versus frequency. The different kind of amplifiers we have seen, that is audio amplifier, wideband amplifier, radio amplifier, DC coupled amplifier, AC coupled amplifier, like that. So for those amplifiers, if it is an audio amplifier, audio frequency amplifier, the frequency response will be like this. Similarly, for the wideband amplifier, the frequency response will be wider like this. And for the radio frequency amplifier, this is the frequency response. What it is giving the information means, in x-axis we will be having a frequency and y-axis we will be having gain. Means for the radio frequency amplifier, we are going to get the gain only at these frequencies. The set of frequencies where the radio frequency amplifier is going to amplify is this. Here we are going to get the maximum gain. As the frequency becomes lower, it is going out of the radio frequency range, that amplifier is not going to amplify. By looking at the frequency response of any amplifier, we can see clearly from which frequency to which frequency the amplifier is going to amplify. And the gain in the amplifier is going to be represented with decibel, that is a logarithmic scale. And always the frequency, the lower frequency is something like this point to this point, we are going to take by reducing the level of gain. If it is the maximum gain is here, we are going to reduce that by minus 3 dB points, and we are going to take the frequency, lower frequency and the higher frequency for the bandwidth. So we will understand why that 3 dB is going to be taken in the other video. Then bandwidth. Bandwidth is the difference between the upper as well as the lower cutoff frequencies. If this is the frequency response and in y-axis we are writing the gain with respect to power, this is the maximum power we are going to get from the amplifier. And the lower frequency the amplifier can amplify is F1, and the higher frequency or the maximum frequency it can amplify is F2. If you get the frequency response like this, by reducing the 3 dB gain over here, this will be the line we are going to get. At this point here, this is F1 and this is F2. If you take the difference between F2 and F1, the amount of frequency range we are going to get, that difference will be called as bandwidth. Bandwidth is the difference between upper frequency to the lower frequency cutoff. So with respect to the voltage gain is concerned, you can observe here AV maximum, and we are taking 3 dB low, that is 0.707 for the voltage. We need to multiply 0.707 for the maximum gain, so that we are going to get the cutoff frequency for the lower cutoff as well as for the higher cutoff frequencies. This is how we can say the bandwidth of the amplifier, by looking at the frequency response. And this figure might be giving the more information, where you can observe here this is the bandwidth, and we are not going to consider these two areas. Why we are considering this as bandwidth means by taking 3 dB lower to the maximum output. This is lower cutoff frequency and this is higher cutoff frequency, and this is the bandwidth. Then we need to understand phase shift. The amplifier output may be having some phase shift with respect to the input signal is concerned. So we are discussing phase shift here. Suppose this is the input signal of any amplifier circuit, and the output signal may be this. Okay, so if we are getting the two phases of the signal like this, we need to get the difference between these two. The timing difference between these two will be represented with the phase angle, and that is the phase shift the output of the signal is taking. Let us understand this in a better way. So these are the different phase shifts signals, how actually they are going to look. If the phase shift is 90 degree, if the signal A is like this, and because of the amplifier the output may be something like this, these two signals will be having a 90 degree phase shift, where A is ahead of B. A is starting early than B with an phase shift of 90 degree, we are going to say. And in other words, we say A leading B with 90 degree phase shift. And similarly here, you can observe it is again a 90 degree phase shift where B is leading A. And if the signal is completely reverse like this, we say it is 180 degree phase shift. And if A and B are in the same phase, we call it as the two signals are in phase with 0 degree phase shift, or it will be a 360 degree phase shift. So we can understand this with this particular waveform. If it is starting from 0 degree going to 90, the signal is going to be changed like this. If the phase shift is 90 to 180, at 180 degree exactly the signal is in reverse order. Again, the next 90-degree phase shift it is taking, so the 270-degree it is looking like this, and once it completes the 360-degree phase shift, it is looking like a previous normal signal. This is how the phase shift of the amplifier can be obtained. You can observe here the first diagram indicating an amplifier output with 0-degree phase shift or 360-degree phase shift. As the input signal is, similarly the output is generating with amplified output. But the second figure you can observe there is an 180-degree phase shift occurred, where if the input signal goes high like this, the output signal will be generating the lower voltage like this. This is how the phase shift of the amplifier is going to be changed. And then the next concept with respect to the amplifier is feedback. What is feedback? Feedback is defined as the process of returning or giving the part of output from a circuit back to the input. Here in the figure you can observe there are two types of feedbacks. One is positive feedback, another one is negative feedback. In the positive feedback, the output is given back through the feedback circuit to the input. The feedback output, the blue wave, it is same as the input signal. If the feedback output is same as the input signal, so we say the feedback circuitry what we have used here, the mechanism is positive feedback. If the feedback output coming to the input is with respect to the input signal, if it's a 180-degree phase shifted, we call it as negative feedback. In the previous topic we have seen the phase shift. Here you can observe when we are giving the feedback output of the feedback circuit may be 180-degree phase shifted with respect to input. So here this is called as negative feedback and this is called as positive feedback. So let us understand the feedback in detail. So in amplifier circuits we are going to use negative feedback always. What negative feedback is going to do? Why we need to give the negative feedback for an amplifier? We can see here these are the negative feedback amplifier advantages. If we give the negative feedback to the amplifier, it stabilizes the gain of the amplifier. It makes the amplifier stabilize and it reduces the nonlinear distortions. It reduces the nonlinear distortions or the noise coming to the amplifier. And the negative feedback circuit increases circuit stability and also it increases input impedance or resistance. While discussing the input resistance, I told input impedance of any amplifier should be high. By giving the negative feedback, we can increase the input impedance. Similarly, output impedance of the amplifier should be low. By giving the negative feedback, we can decrease the output impedance. Similarly, it reduces the noise level. As I said, the second point reduces the nonlinear distortion. It also reduces the noise level coming to the amplifier and it improves the frequency response as well as bandwidth. If the bandwidth of the amplifier or the frequency response increases, what happens? The different kind of frequencies also the amplifier can amplify. If the bandwidth of the amplifier is less, only particular frequencies the amplifier is going to able to amplify. That's why bandwidth should be always larger and noise factor should be always less. Input impedance should be high, output impedance should be low, and it should be able to address the nonlinear distortion and it should stabilize the circuit and gain. So these are the advantages of the negative feedback. It will be helpful for an amplifier. That's why we use negative feedback in amplifier circuits. Where we use positive feedback then? We are going to use positive feedback in oscillator circuits. While designing oscillators, we come to know the positive feedback arrangement in oscillator circuits. The derivation of overall gain of the amplifier with negative feedback. We know that gain of the amplifier can be written as A is equal to V0 divided by V in. Suppose if the feedback is connected, what happens? We will see. So now we can write the overall gain with the letter G. We can represent that with G, that will be equal to V0 divided by Vs. And the amplifier gain without feedback is A, that is equal to V0 divided by Vi. You can observe here, this is Vi and this is Vs. This Vi is the input coming to the amplifier. For this particular amplifier, input and output is considered as V0 and Vi. That's why gain A is V0 by Vi. Overall gain, if we take the circuit gain, that is V0 divided by Vs. So by this expression, we can write it as V0 is equal to A into Vi. Now, what is Vi here? Since it is a negative feedback, we know that the feedback circuit is inverting the signal coming from the output side. Inverting in the sense the phase shift of this signal with respect to the input is 180-degree phase shift. That's why, since it is a negative feedback, we need to subtract the voltage coming from this feedback network here. That's why Vi will be equal to Vs minus Vf. What is Vf here? Vf is the output of the feedback circuit and V0 is the input here. This is V0 and beta is the feedback factor. That's why Vi can be written as Vs minus beta times V0, where beta is Vf divided by V0 and it is feedback factor. And we can write the expression for Vs by using these two. Now Vs is equal to Vi plus Vf, that is beta times V0. Now we can use this Vs expression as well as V0 expression. We can put it here in the equation 1. If we substitute equation 2 and equation 3 in equation 1, it becomes G is equal to A into Vi divided by Vi plus A beta into Vi. In this expression, we can take Vi here and in the denominator we can take Vi as common. So if we take Vi as common in between these two, Vi get cancelled and the overall gain expression becomes A divided by 1 plus A into beta. Now this is the overall gain of the circuit including the negative feedback. Without negative feedback, what is the gain? A is the gain. With negative feedback, what is the gain? A divided by 1 plus AB. Now what we are going to understand here, this is the overall gain of the circuit, where by including the negative feedback, what happens? It becomes A divided by 1 plus AB. Now if we observe, the denominator term is more than the numerator. So compared to A, now the overall gain is reducing its value once we connect the negative feedback. Therefore, negative feedback reduces the gain. Gain of the amplifier is reduced by using the negative feedback. But because of the advantages what we have discussed in the previous topic, we need to go for negative feedback for the stability of gain, for noise reduction, as well as bandwidth, widen bandwidth, and the reduction in the nonlinear effects. We need to go for negative feedback. But negative feedback reduces the gain of the amplifier. We need to compromise with the gain and we need to get the advantage of bandwidth, noise and all. That's why we need to use the negative feedback. So overall gain of the amplifier with negative feedback is G is equal to A divided by 1 plus AB. Then we have multi-stage amplifiers. So the previous thing what we have seen is one-stage amplifiers. If you use multi-stage amplifiers, what happens? In order to provide sufficient large voltage gain or large value of gain, we can use the amplifiers in multi-stage. Means we can couple the amplifiers one after the other so that we will be getting high gain. And then the overall gain of the amplifier will increase as several stages are going to increase. It is just a product of those amplifier gains. If you use 3 stages, the overall gain AV is equal to AV1 into AV2 into AV3. This is how we can increase the gain in terms of products of individual stages. But the bandwidth of the multi-stage amplifier is going to be reduced compared to the bandwidth of individual stages. Here, gain and bandwidth are vice versa. If gain increases, bandwidth reduces. The bandwidth increases if gain reduces. Here is the example of a two-stage amplifier. This is RC coupled common emitter amplifier, where you can observe this is the first stage and this is the second stage. Here we have used a bipolar junction transistor and a voltage divider circuit. By providing input here, we are going to get the output in this point. And we are using a capacitor here. C3 is going to couple the two stages. And the second stage, you can see here, it is just a replica of first stage. And this is the output we are going to get from the second stage. By connecting the amplifiers like this, we can increase the gain of the amplifier. There are different methods of multi-stage connection or coupling, we can say. The first method is RC coupling. Here we are going to use the resistor as well as capacitor arrangement in between the first stage and the second stage of amplifiers. Here we are going to couple using capacitor as well as the resistor. So RC coupling is one of the major method we are going to use, widely used method for coupling of multi-stage amplifiers. And then we have LC coupling. LC coupling in the sense we are going to use inductor as well as capacitor. Here we are going to use this kind of coupling while RF as well as high frequency signals are going to be amplified. And then we have transformer coupling. Transformer coupling in the sense for the coupling of two stages we are going to use transformers in between. Here there will be no power loss in collector and base resistors. That is the advantage of transformer coupling. Here because of the transformer, if you use the transformer coils and the number of turns carefully, we can increase the amplifier gain to the higher level. And then we have direct coupling. In direct coupling, we will be not having any extra circuitry in between the two stages. Just we will be having a supply for the amplifiers, so that here it is less expensive. Less expensive because of no extra circuitry is included other than the amplifiers. These are all the different methods of coupling. So here we have discussed starting with amplifier and then the amplifier characteristics such as gain and then bandwidth, frequency response and negative feedback. Negative feedback is required for the amplifier and the advantages, and then different methods of coupling. Thank you.